Let's jump back into our review. This is a review on Unit 3, which is physical science. Remember, physical science is the opposite of life science, which is what all the stuff we did on human body and plants and soil were. So that was all life science. Now we're looking at the opposite. So this is science that deals with non-living things, such as space, energy, such as light and sound. You did sound in second grade. And then, of course, this year we focus on force and motion, especially, okay, and the states of matter. Do you remember the lightsaber fight that Ms. Benton and Ms. Tiller had? Which one of us was right? Do you remember? What is a force? Remember, the force be with you. What did Yoda say? A force is a push or a pull or even a twist. One of the main forces we talked about first was gravity. And remember, when we said gravity, we did that thing where we said gravity pulls us down or brings us down. So you can say that with me. That picture is Isaac Newton, and he's the man where the story goes that an apple fell on his head, and it made him start wondering why. Why does everything fall down like that? And he ended up explaining gravity to people. Friction is when something rubs up against something else. Friction helps slow things down, and it can also create heat as things rub together. Friction can be helpful, like the brakes on your car. When you want to stop, the brake actually rubs up against the wheel, and that helps slow it down, which is obviously a good thing. You have certain shoes that give you good friction on the floor, and that's why when you take a step, you can push off the floor without slipping and sliding like you're on ice all the time. Especially good if you're playing sports. But sometimes friction can be kind of annoying, like when you have a shoe rubbing against your skin and it causes a blister, which hurts. Or if you're trying to play with a toy car and your car keeps slowing down because you're on the carpet. So friction is a force that engineers understand, and they use what they know about it to help them in creating things or trying to find ways to lessen the friction, especially with things that they want to not rub up against each other. If you remember, we use little toy cars on those little ramps, and we tried it on the tile floor and the carpet. So this is a picture of a couple cars at my house on my tile floor and also on my carpet. Let's say that both cars are on a flat surface and we push both cars with the exact same amount of force. Which one of those cars, the blue or the red, is going to go farther? Say it. Which one's going to go faster? Why? I hope you said that the blue one would go faster, which would also help make it go farther as well, because it's on the smooth surface. And so using the science words for it, there's less friction. The carpet makes a lot more friction, which slows that red car down faster. All right, after we did all of the tests with the cars on the ramps and the floor, we started talking about matter. And remember, matter is all the stuff in the world. It's just stuff. To be more specific, matter takes up space and it has weight. And what makes it tricky is sometimes we think about things that we don't really see, or we think they don't weigh very much. But even if they don't weigh very much or we can't see them, they're still there. It's still matter. We looked at these pictures that you see here. All of those things are examples of matter. Everything there is matter. Even the smoke, even the old decaying leaf, even the clouds that you can't really touch, but they're there. What are the 3 different states of matter? Can you say it out loud? I hope you said solids, liquids, and gases. Matter can change from one state, we call it a state, like the form that it's in. It can change from one state to another. But something I want you to remember is that matter never ever just goes away. It might change state or form. You might not even be able to see it, like when water evaporates into the air, but that water didn't go away. It's not gone. It doesn't just disappear. It's still there, just in a different state. We call that conservation of mass or conservation of matter. And this is actually what we were just working on as schools closed up. So I want to try to remind you of this. The word conserve means to save or to keep. So when you conserve the mass, which is like the weight of something, or just matter, scientists use both terms, either one is fine. That means that they're just keeping their mass or their matter, even if it doesn't look the same. If you remember the balloons, I think Miss Leone did this one with a few classes. The one that was filled up with air was actually heavier on the little ruler that we used. Even though you don't see the air inside of it, it's definitely there. You can see the shape of the balloon, but you can also measure and see that it weighs more than the balloon that doesn't have the air filled up inside. Remember, we also did the little cup tipped over upside down in the tub of water, and the paper towel inside stayed dry because the air in the cup pushed the water away. And that was proving that that air in the cup still took up space, even though you couldn't see it. And I remember a lot of you said that cup was empty. But if it was empty, the water would have gotten inside it. And instead, the air actually pushed the water out. That was an activity you could actually try at home. These are some things down here that I wrote. I want you to remember about matter. Air always has weight, even though you can't always see it. It's invisible. Matter still takes up space, even when we can't see it, like in the empty cup. Or not the empty cup, I'm sorry, the cup. And matter never disappears. We just might not be able to see it. It's still there. So I want you to watch this video next and see some of the examples of how matter can change state or shape, but it doesn't actually go away. That matter is still there and it still has weight. So go ahead and watch this video. Hey scientists, I'm looking at you third graders. We are working today on a concept called conservation of mass. Some of our classes at Benton Heights already did this lesson, and some of you haven't. So if you have, this is a great review. If you haven't, pay close attention. Think about the word conserve. If you've ever heard that word, I know sometimes we talk about like conserving paper, conserve water, conserve energy. It might make you think about saving or keeping. And that's pretty much what conserve means. So conservation is when we talk about conserving or saving something. And in this case, we're talking about the mass or what's in the matter, the stuff that we're talking about, like what it's made out of. Most of the time when we measure mass, we think about weight or how heavy it is. So, because of that, we're going to do an experiment today using a scale, and we'll actually measure how heavy things are. We are trying to see if the weight or the mass of different pieces or different types of matter is still saved even when we can't see it anymore or when we put things together or take them apart. All right? So here's what we're going to do to demonstrate this first. I have a cup of water here, and I sketched a quick picture. If you have a notebook or some paper, you can do this too. It's a good way to jot it down and remember it. So there's a cup of water, and I've labeled it. And then I have a smaller little cup with salt in it, okay? And I've labeled that. We are going to weigh each of those two materials and write the weight down under the labels on our picture. So if my videographer will zoom in on the scale, you can see that All right, when there's nothing on it, it is at 0. And if you need to, zoom all the way in so you can see the numbers maybe. So we're gonna weigh our cup of water, and it is 138 grams. A gram is about the weight of a paperclip, if you don't remember that. So think about holding a paperclip. That's about 1 or 2 grams, so not very much weight. This cup of water is 138 grams. So I'm going to add that to my work here. A G for grams. All right, the salt in this little cup, that is 10 grams. Label that. And now, as I'm sure you have already figured out, we're going to mix them together. So we'll put the salt in the water. Stir it up a little bit. And you should remember from 2nd grade, what is the word for it? What's happening to the salt when it's getting kind of broken into smaller pieces and mixed into the water where we can't see it anymore? I hope you said dissolved. The salt is dissolving in the water. All right, it's a little bit cloudy right now, but as it stops moving around, it will settle and clear. But you really can't see the actual salt. It's gotten pretty well mixed in or dissolved into the cup of water. So I want you to take a guess. This is your smart guess or hypothesis. What is the weight going to be of our mixture here? You may even see where I could add them together. I'm going to put like a plus sign and sketch a new picture. So here is my water with the salt inside. Little pieces of salt mixed in. So this is salt water. Whoops. This is our salt water, just like what you find at the ocean. All right, any guesses about what you think the final weight is going to be? Is it going to be more than what the water weight started out as? Is it going to be less than that, 138 grams? Or is it going to be exactly the same? We still have our cup of water. Is it going to be exactly 138 grams? Let's check and see if you're right. When I weigh this, I am also going to weigh this little cup, because when we did our weight the first time, we weighed this cup that had the salt in it. And to keep everything accurate, we need to still count that, but it's empty. Remember, the salt is now in here. All right. Whoop, it turned off on me. And it is 148 grams. Let's take a look at that, scientists. What do you notice about the weight of the water, the cup of water we started with, and what we have now? It went up exactly 10 grams. Even though we don't see the salt in the cup anymore, we know it's still there. You watched me put it in there, and if we really wanted to, if I took a drink of this, I would really notice the salt is still in there. I'm not going to, I think that's disgusting. But the mass, or the amount of material inside the matter we're talking about, is still there. It's still inside. We've put it into the water. Even though we don't see the tiny pieces of salt, it's still in the water, and the mass hasn't changed. The mass is still the same of each part, and when we put the two parts together, it just adds up those two weights. So that's an example of conservation of mass. Let's do one more. In this one, I have some little blocks that hook together. I've got 1, 2, 3, 4, 5, 6, 7 orange ones and 4 black ones. So let's weigh each part All right, the 4 black blocks are 12 grams. Just gonna jot that on the side here. 12 grams. All right. Anybody want to take a guess how many or how much weight is on the 7 orange ones? Let's see if you're right. 21 grams. All right, based on what you now know already about conservation of matter or mass, based on what you know about the conservation of mass, how much are all 11 cubes going to weigh? Let's hook them all together. And the total weight is 33 grams. Think about how we got 33 grams. It's almost like an equation. 12 plus 21 equals 33 grams. What if we broke them all into pieces? Do you think they weigh less when they're all separated out? Let's see. Still 33 grams. Friends, that's an example of conservation of mass. The mass of something does not change. Even when it changes shape or form. If a solid turns into a liquid or a liquid turns into a gas, the material or the matter is still there. The same amount of mass is still there, even if it changes form. All right, we'll stop here for today. Go explain conservation of mass to somebody else at home. And you might even be able to try something like this. Have a great day, guys. Bye. Class that didn't get a chance to actually do this before we left school. So hopefully that made sense to you all and was a good review of how even though we can't see the salt in the water, or we took those cubes apart in different pieces, matter is still there. It might change shape, it might change state, it might look like it goes away. It doesn't, it just changes. It's still there, it still has weight. All right, this was the last part of our physical science unit that I was planning to do that next week, right when schools were closing up. So this is heat transfer. The word transfer means move from one place to another. If something transfers or transports, it's moving from one place to another. So this is how heat moves. Now I'm going to say something you're probably going to think is kind of crazy, but I promise it's true. There is no such thing as cold. It's true. No such thing. Cold is simply a word that we use to mean there's no heat or the absence of heat. Heat is a real thing. It's an energy. Cold is not. Cold just means no heat. So since cold isn't real, cold can't actually move. So we know that heat is the energy that's moving and changing. Heat always, always, always transfers from something warmer to something colder. And you can see in that funny little picture, it says hot to cold. That's a good way to remember it. It moves from the hot thing to the cold thing. So if you touch an ice cube, your body is warmer than the ice cube. So heat leaves your body and moves to the ice. That's what would make the ice actually melt, especially if you were holding onto it in your hand. It makes your skin feel cold because some of your heat is moving to the ice. It's actually leaving your body. On the other hand, if you touched a hot stove, the stove is hotter than you are, so heat would leave the stove and go to your body, to your skin, and cause a pretty bad burn because it's awfully hot. Ow! Watch this fun video to help you remember and understand a little bit about how heat transfers.
from hot to cold. From hot to cold. Heat transfer goes from hot to cold, from hot to cold, from hot to cold, from hot to cold, from hot to cold. Heat transfer goes from hot to cold, from hot to cold, from hot to cold, from hot to cold, from hot to cold. Heat transfer is really neat. It always goes from hot to cold. You'll always remember this, kiddies, even when you're getting old. When you go out to dinner, you want food that is super real hot. But if you wait too long to eat, oh, you'll be so sad with what you got. See what happens, it's really easy. The food is sitting out and touching the air. The heat from your food's not disappearing, it's being transferred to the air. Cause heat transfer is really neat. It always goes from hot to cold, from hot to cold, from hot to cold. Heat transfer is really neat. It always goes from hot to cold, from hot to cold, from hot to cold. Now summertime and you're at the pool, jumping off the high dive. Once you hit that cool water, it feels like you're frozen alive. See what happens, it's really simple. Your body has a warmer temperature, cause once you touch that cooler water, it's taking your heat energy for sure. Heat transfer is really neat. It always goes from hot to cold, from hot to cold, from hot to cold. Heat transfer is really neat. It always goes from hot to cold, from hot to cold, from hot to cold. Thermometer is a tool we use to measure heat energy. It measures particles' movement. They're moving endlessly. When molecules gain heat energy, they move around faster. The liquid expands and the temp goes up on the thermometer. Cause heat transfer is really neat. It always goes from hot to cold, from hot to cold, from hot to cold. Heat transfer is really neat. It always goes from hot to cold, from hot to cold, from hot to cold. Grab some different objects sitting in your room at home. Some feel cooler while others are warmer, but they have the same temperature. So the reason is that some objects conduct energy better than others, meaning it takes energy easily. We call these things conductors. The objects that warmer, we call these insulators. They don't conduct energy that well, so I'll see y'all later. Heat transfer is really neat. It always goes from hot to cold, from hot to cold, from hot to cold. Heat transfer is really neat. It always goes from hot to cold, from hot to cold, from hot to cold.
So hopefully that helps you remember. Hot to cold. Heat transfers from the warmer thing to the colder thing. So that kind of wraps up our physical science unit and wraps up this week of science. Next week, definitely check in on all the materials that we put up. We're going to start looking at our 4th unit, which is the last science unit of the year, and that's earth science. So we're going to be learning about landforms on the earth and different bodies of water, as well as the earth in space. And some of you have even asked me some questions about what makes it look like the sun moves across the sky, what makes shadows. Does the earth move? Does it turn? We talked about it rotating around. What does that mean exactly? So we're going to talk about all those things, learn about space and a little bit about the solar system. Should be pretty cool. So I hope you'll check in. I miss you lots. So does Miss Benton. I want you to know that your science teachers miss you a whole lot. I left a link for you for a read aloud about roller coasters and another link for the force and motion vocabulary words. At the top of that document, there are some suggestions of things that you can do to try to learn or remember all those good words. Maybe someone at home will help quiz you on what those words mean. It's good practice for your brain, so make sure you check those things out as well, okay? That's it for our week. That's it for that unit. Next week, we're going to be looking at Unit 4, which is Earth Science. And you will be looking at landforms on our Earth and bodies of water. And then we're also going to look at Earth in space, how it relates to the moon and to the sun, how they work together. Some of you have been asking questions about if the sun moves, how the Earth goes around the sun, what causes day and night, what causes shadows. Those are all things we're going to look at in this last unit. So make sure you check in and pay attention to all that good stuff. On that note, I want you to know that Miss Benton and I miss you so much. This is not at all the way we ever expected to be doing teaching, and we definitely miss getting to see you and be with you every day. But I'm glad we have this technology to at least help us connect a little bit. Please know I'm thinking about you a lot, and I hope you have a great weekend. Bye, everybody.